Moving on, we have Simon Banville from Natural Resources Canada. He will be talking about Repro3 PPP-AR products. And Simon, I believe you have the virtual floor.
Okay, right. So I'm Simon Banville from NRCan, also the chair of the PPP-AR working group. And today I'll explain how we're generating PPP-AR products for Repro3. We'll start with a little bit of context. There's already several analysis centers who now provide code and phase biases that allow for precise point positioning with ambiguity resolution. So a couple of years ago, the IGS has created the PPP-AR working group to first test the interoperability of the PPP-AR products, and now to generate the combined products. And Repro3 really is the perfect framework to test the combination over an extended period of time. The way the satellite clock combination currently works is that it first ingests the combined orbits and the solutions from the different analysis centers, which includes the clock and the orbit files. The orbit files are needed to apply correction to the clock to make them consistent with the combined orbits. But then, as you can see, the combination doesn't take into account the code and phase biases that are provided by some analysis center. And for this reason, it's not possible for users to do PPP-AR solutions with the current IGS orbit and clock products. So what we're proposing is to do not only a satellite clock combination, but a clock and bias combination, because the consistency of the clocks and the biases needs to be preserved to achieve PPP-AR at the user end. So now analysis centers will not only contribute clocks and orbits, but also biases. And with that, we'll be able to do different types of combinations. So not only clocks, but now combinations of different types of biases, such as the differential code biases or the wide lane, also known as the Melbourne-Fubina biases. And then there's another process that will take the outputs from all of these different combinations and do a transformation that will give us a set of consistent combined clocks and what we call observable specific biases. And it is the use of these clocks and biases that will enable ambiguity resolution for users. I know I've just skimmed through this process really quickly. For those of you who wish to have more details, I'll refer you to the paper that's mentioned here at the bottom of the screen. One last thing I wanted to say about this slide is that we're also encouraging analysis centers to provide attitude in the Orbex format, but I'll say a few words about this soon. But first, I want to just introduce the bias Sinex format, which has been adopted by the IGS to provide these code and phase biases. So as you can see in this example, we have for each satellite a bias for each observable type. So it's very simple for users. They only need to apply these biases directly into their observations. And the nice thing about them is that they remain valid whether you're processing uncombined or linear combinations of observations. So whatever your processing strategy is, you should be able to do PPP-AR with these biases. The other novelty with the combination process is the exchange of satellite attitude information. The IGS has opted to exchange this information in the form of quaternions in the Orbex format. The way that works is that those quaternions allow to define the rotation matrix from the Earth-centered Earth-fixed frame to the satellite body frame, which basically gives the attitude of the satellite in space. Now, it doesn't really make sense to combine attitude from different analysis centers. So if we want to provide attitude product with the combined orbits and clock products, we need what I call here a reference attitude. And so far, we've been using the Technical University of Graz open source software groups for this purpose. It includes all GNSS attitude models. And really, as a side note, if you haven't checked this software on GitHub, I encourage you to do so. It's a quite impressive piece of software. Now, one thing that I haven't mentioned yet is why we need to exchange satellite attitude information. Well, it's been known that there are issues when combining satellite clocks of eclipsing satellites. What this plot here shows is The differences between the satellite clocks provided by each analysis center and the combined clock product. And we see there's clearly a satellite here that's sticking out in red, and this is G25, which is a Block 2F satellite that's observed at a beta angle close to 0 degree. And for those of you who are not familiar with this terminology, the beta angle is the angle between the orbital plane and the sun. So as this angle gets closer to 0, satellites have to go through the Earth's shadow once per revolution. And in the Earth's shadow, some satellite types are known to make some unpredictable turns. And when the analysis centers model these turns differently, it causes discrepancies in the satellite clock estimates that are due to the carrier phase wind-up effect. But if we have access to the attitude that was used by each analysis center when they computed their satellite clock corrections, then we're able to apply a correction to mitigate these inconsistencies. Now you'll see that there are still some remaining effects that are due here to the satellite phase center offsets that are propagating to the clock estimates when the satellite is not oriented correctly. But there's currently no way to remove these remaining inconsistencies. The only way would be to have all analysis centers use the same attitude, which from my understanding is currently not possible given constraints on some of the force modeling for the orbits. Now that we have a better understanding of the combination process, we can look at the products that we have available for Repro3. There's 9 analysis centers who contributed satellite clock corrections. However, 3 of them provided 5-minute clocks at 5-minute intervals, which really corresponds to only 10% of epochs. So for this reason, I did not include them in the clock combination for the test presented in this presentation today. There's also some analysis centers who did not provide attitude information. This I don't consider as being as critical. I have the feeling that if the attitude of that analysis center does not agree with the other one, they'll most likely get downweighted a little bit in the clock combination process for eclipsing satellites. In terms of phase bias availability, we have 4 analysis centers who provided phase biases for GPS, 1 for GLONASS, and 3 for Galileo. If we consider that we need at least 3 analysis centers for a proper redundancy for a combination, then that means that we would be able to provide in Repro3 the GPS L1 and L2 phase biases starting in the year 2000, day of year 124, which is the day where selective availability was turned off. And for the Galileo L1 and L5 phase biases starting in the beginning of 2017. Now we can look at an example of the satellite clock and bias combination to get more insights into the process. We'll look at 1 week of data in 2018. We'll consider satellites from 3 constellations, GPS, GLONASS, and Galileo, and products from the 6 analysis centers who contributed the 30-second clocks. I used the combined orbits produced by Selim, the IGS-1 solution. The reference attitude was provided by groups, and also did some PPP tests using 100 globally distributed stations, and those tests were done using the NRCan PPP software. These PPP tests, the reference station positions came from the SINEX combined solution produced by Paul Revichon. So one aspect that's interesting within the combination is to look at the consistency of the wide lane or the Melbourne-Vubena biases. On the left, we have the 4 analysis centers who provided phase biases for GPS. And on the right, the 3 analysis centers who provided phase biases for Galileo. And what these plots show is basically the difference between the wide lane biases of each analysis center with respect to the combined products. And we see a really good agreement between analysis centers. We have residual RMS in the range of 2 to 3 centimeters for both GPS and Galileo. So really that shows the great consistency between the analysis center solution. If we move on to the clock combination residuals, we have the residuals for GPS on the left, GLONASS in the center, and Galileo on the right. And for GPS and Galileo, I've been combining here what I call integer clocks, and this is the clock corrections plus the ionosphere-free phase biases. But now it's important to mention that all analysis centers contribute to the clock combination, even if they don't provide phase biases, which in this example was the case for ESA and JPL. It's just that the integer properties of the combined clocks will only come from the analysis centers with phase biases. And in terms of residuals, we see that we have a residual RMS of about 2 to 3 millimeters for GPS, which is as expected. And interestingly, we get pretty much the same thing for Galileo. So that's very good news. In this particular example, there was one satellite with some modeling issues, but overall, most of the satellites behave very well. For GLONASS, a different story. For those of you who wonder why the IGS is not providing a combined GLONASS clock solution, well, we kind of have the answer right here. There's just different signals between solutions, and it's complex to combine without obtaining a solution is actually worse than the solution of each individual analysis center. But we included the combined GLONASS clocks in our test just for testing purposes. And also ran some PPP results using these combined orbit clocks and biases. And those are results for 24-hour static sessions. We see the RMS error for the north, east, and up components. And this is based on 700 solutions. I use different configurations of GNSS using the typical letters G for GPS, R for GLONASS, and E for Galileo. But here I've used lowercase letters to indicate solution with float ambiguities and uppercase letters for solutions with fixed ambiguities. And really the takeaway from this plot is the benefits of ambiguity resolution for both GPS and Galileo. For instance, you can look at the east component and compare the float and fixed solution for GPS in the black and red bars, or for Galileo in the green and purple bars. So we see a clear improvement that is due to ambiguity resolution. And surprisingly, the lowest RMS error is the multi-GNSS solution with ambiguity resolution in brown. And I say surprisingly here because I was really expecting GLONASS to corrupt the solution a little bit, which is typically what happens. I'm not sure why that solution is actually a little bit better here. Perhaps it's just luck. It's just based on 1 week of data. But we'll need more analysis to confirm what's the real contribution of using GLONASS in the PPP solution. So in summary, it looks like we'll be able to provide phase biases that enable PPP-AR in a Repro3 starting in 2000 for GPS and 2017 for Galileo. This presentation today showed the proof of concept that yes, we're able to generate integer clocks for GPS and Galileo. We're able to use these clocks in PPP to do ambiguity resolution, and it looks like the ambiguity resolution is beneficial and improves the accuracy. Now, obviously, that was based on 1 week of data only. I think that our next speaker, Dr. Gang, will be providing more PPP results from his group. And as I mentioned, there's more work that is needed to determine how to incorporate the GLONASS satellite clocks into the combined products. And I'll end on a little call for participation. If anyone's willing to contribute either time, expertise, or even CPU to help the IGS PPP-AR working group, well, feel free to contact me. We have a lot of things to do and very, very few people to do it. So if you want to join us, you're more than welcome. Thank you very much.
All right, thank you very much for that amazing presentation. Do I have any questions for Simon? Okay, so not for now, but please feel free to continue asking questions. I have a different question here for Celine and Paul on the chat. We'll move on and come back with additional questions for Simon. Thank you again so much for your presentation.